Hi, I'm Sarah Witter with the Cadeo Group, and I'm here with my colleague Nate Baker to share some research we've recently performed in collaboration with the National Electrical Manufacturers Association, NEMA, and Northwest Energy Efficiency Alliance, NEA, investigating the benefits of power drive systems across a variety of applications. We've spent the past several years working with NEA and other agencies to conduct research to better understand pump energy consumption in operation, as well as develop new metrics to better describe their energy performance and work with end users to improve efficiency in pump systems. This work is born out of NEA and NEMA's combined interest in realizing the energy savings potential from more efficient motor systems, including systems with variable speed capabilities. While the use of adjustable speed drives and appropriate sensors and controls, or power drive systems, offers significant energy savings potential in commercial and industrial applications, they have traditionally been installed in variable load applications, such as heating and cooling systems responding to variable climate conditions. And many believe they only save energy or are cost effective in these types of applications. The goal of this research was to better understand the energy and non-energy benefits associated with power drive systems in both constant and variable load applications, and particularly understand if power drive systems were cost-effective in constant load applications. Now I'm going to hand it over to my colleague Nate to talk about the specifics of the analysis.
While the universe of motor-driven loads is vast, we had to start somewhere. So to perform our analysis, we started with recent data collected by NEA on pump performance in the Pacific Northwest. We used data on 132 pumps from that work, incorporating pumps that had sufficient characteristic and operational information to effectively characterize load profile and energy consumption in both constant and variable speed applications. Using these data, we explored three main topics. One, the specific load profiles observed in different applications and how variable or invariable they were. We did this to determine if there were any inherently constant or inherently variable load applications. Two, the energy savings associated with power drive systems across these applications and load profiles. And three, the observed application or penetration of power drive systems among these different applications. While these data only include pumps, the general findings can be expanded to other similar motor-driven products like fans and compressors. To perform this analysis, we first investigated the load profiles observed in the data and categorized them into constant load and variable load systems, where constant load systems spent 90% or more of their time at one load point, and variable load systems demonstrated more variable operation. Note that these characterizations are purely related to the load the pump is serving and are independent on whether the system is equipped with a variable speed drive or not. The first thing we observed was that there were no applications that were inherently constant load and demonstrated no variability. Some applications are more variable than others, but there are opportunities for savings from power drive systems in all applications. Next, we looked at what type of applications and system drives are being installed on. That is, we analyzed how many pumps in our sample were equipped with a drive for both constant and variable load systems in each application. Categorizing the data into these four buckets, it was evident that drives are being installed on systems, regardless of the system variability. In the data set we analyzed, 43% of the pumps equipped with power drive systems operated with constant loads. This indicated that while the energy savings may be lower for constant load pumps, the benefits of a power drive system are still large enough to justify installing in many cases. Having considered each pump as serving either a constant or variable load, the second question we investigated focused on understanding the energy savings associated with installing power drive systems on pumps serving those different load types. To calculate energy savings, we modeled the operation of each pump as if it were controlled in two different ways. Either by constant speed control, with the system throttled to meet the specific load point, or served by a power drive system, where the necessary load could be met by varying the speed of the pump and allowing the pump to operate along the system curve. The pump data used for this analysis included information on the pump performance curve, which represents the relationship between flow, pressure, and power for a specific pump. Using this information, along with the pump's load profile, we calculated the annual energy consumption by multiplying the power draw at each load point by the number of operating hours spent at each load point. This represents the energy consumption of each pump when its load is met without speed control. Modeling the energy consumption of a pump with a power drive system was a bit trickier. When the speed of a pump changes, the pressure and flow don't follow the performance curve, but instead they track down the system curve, which is defined by a set of physical principles called the affinity laws. The system curve is dependent on two variables, static head and full speed operating point. Static head is the amount of pressure a pump must overcome to initiate flow, and is usually proportional to the vertical distance between the inlet to the pump and the discharge of the system. This pressure can range from 0 feet of head in closed loop systems to really high values in systems that include a large vertical lift. For this analysis, we assume the closed loop systems had 0 static head. Commercial cooling towers and pressure boost systems had a static head equivalent to 35% of head at the pump's best efficiency point, or BEP. And industrial and municipal pumps had static head equivalent to 22% of head at BEP. These static head values are averages observed through NIA's research into pump operation. Full speed operating point represents where the pump would naturally operate at full speed without any system throttling. That is the point where the performance curve and the system curve intersect. Because the available information differed from pump to pump in NIA's dataset, there were a couple methods we used to determine the full speed operating point. If a pump was equipped with a variable speed drive and data on pump speed was available, the flow at full speed was calculated using the affinity laws. If the pump was equipped with a variable speed drive, but speed data was not available, the maximum observed flow rate was established as flow at full speed. For constant speed pumps, we based the full speed operating point on BEP. Using information collected by the Department of Energy, we established a full speed operating point at 92.5% of BEP. For constant speed pumps with a maximum observed flow rate below this value, full speed operating point was set at 92.5% of BEP. For pumps with a maximum observed flow rate above 92.5% of BEP, the full speed operating point was established at the maximum observed flow rate. For this information, we could then calculate the annual energy consumption of the pump with variable speed control, similar to how we calculated it for constant speed control, by estimating the input power at each load point and multiplying those input power values by the amount of time the pump spends at each of those load points. The energy savings for installing a power drive system on any given pump is simply the difference between the constant speed energy consumption and variable speed energy consumption.
Thanks, Nate. Let's take a step back here and unpack how power drive systems can facilitate energy savings in both variable load and constant load applications. For variable load applications, the power drive system allows the pump to more efficiently meet the load requirements, decreasing unnecessary system pressures and decreasing power draw. This is the energy savings mechanism most often thought of when power drive systems installation is considered. The energy savings for constant load systems are a little more nuanced. As Nate reviewed, the system curve is defined by static head, which impacts how much the drive can turn down while still meeting the system requirements, as well as the full speed operating point, which represents where the pump, as installed, would operate with no artificial head in the system. As the chart on the slide shows, the full speed operating point is often at a slightly higher flow rate than the intended design flow due to the tendency of design engineers to specify robust and conservative designs that will ensure system performance is provided, despite any uncertainties that might occur during construction or installation. This almost always results in an oversized pump, but for completely logical and appropriate reasons, since it's much easier to adjust a pump that is slightly too large than address one that's too small. People don't notice if they have an oversized pump, but they certainly won't be happy if they have an undersized one. With a constant speed pump, the design flow is achieved during system commissioning, typically by throttling the pump using a balancing valve. With power drive systems, however, the design flow can be achieved more efficiently by simply slowing the pump down. This makes power drive systems an excellent design choice because it can mitigate some of that design variability and ensure efficient and flexible operation across a range of flow rates and system conditions that might be found in the field. This also has the benefit of adding a bit of future-proofing to the system. As production requirements change over time, power drive systems can adjust so that energy use is optimized whether the system is needed at a higher or lower level than was originally specified in the design.
Let's keep those two savings mechanisms in mind when we're looking at the energy savings from installing power drive systems. From an application perspective, a power drive system creates energy savings for both variable and constant load systems in all applications except municipal water treatment, which saw a large energy savings potential for variable load systems, but no savings potential for constant load systems. This difference for municipal water treatment could be driven by two factors. The first is related to pump application and the fact that pumps are a main piece of equipment in municipal water treatment plants. These facilities dedicate a lot of resources to ensuring efficient pump operation because it is so closely tied to the facility's purpose. The second factor is related to the data used for this analysis. The sample size for constant load municipal pumps was small, and the smaller the sample size, the more impact individual site has on the average. The municipal treatment savings values are probably impacted by a combination of both a small sample size and a tendency for municipal pumps to operate more efficiently.
From an aggregate perspective, our analysis found that, on average, variable load systems see higher savings, but there is significant savings potential in both constant and variable load cases, as you can see on the slide. We also found those cost savings to be cost-effective, with payback periods of less than a year based on current drive costs and an assumed price of electricity of 12 cents per kilowatt hour, which is the national average. These energy savings are very compelling, but with the analysis dependent on system head and full speed operating point assumptions like we talked about before, differences in those two variables have the potential to impact the energy savings potential that we calculated. We used a sensitivity analysis to investigate the impact of variations in static head and full load operating point on our findings. Our analysis showed that on the pumps included in this study anyways, static head had a larger impact on the energy savings than full speed operating point, but neither of these variables changed the overall conclusions. We found static head to be more impactful because the pumps in the study spend a lot of their time operating at low flow rates, which means that fluctuations in static head have a greater impact on the relationship between flow and pressure, increasing the variability in energy savings.
While the energy savings did vary in the sensitivity analysis, the high-level findings of constant load systems represents a viable option for power drive systems.
Really good point, Nate. And in addition to the energy savings, power drive systems can also provide a number of additional benefits, including decreased maintenance from soft starting and reduced wear and tear on the equipment, as well as a number of process improvements, such as improved controllability and visibility into the system, reliability, reduced maintenance, future-proofing of the system, and IoT connectivity control. These benefits can allow for more flexible system operation, increased production, and the potential for a more advanced connectivity and especially demand response, which is very popular these days. These benefits are especially important in industrial settings and can sometimes outweigh the energy savings of drives. While these findings demonstrate real and compelling reasons to consider power drive systems across a range of applications, more work is needed to further evaluate the right sizing benefits of power drive systems by working with commissioning agents and test and balance contractors to better quantify the level of throttling current control practices that is occurring in the field. We also think these pump-specific results are representative of the likelihood of savings from other variable torque loads like fans and some compressors. However, we would like to do independent analysis of these different equipment types to better account for any operational differences. It will also be important to consider the benefits of power drive systems for non-variable torque loads, where non-energy benefits may play a larger role in determining cost effectiveness. Finally, as we move forward, it will be important to consider the differences in efficiency and performance of different drive systems and ensure that power drive systems are all providing the same level of performance that we expect. We're looking forward to continuing to develop and share these results. If you're interested in finding out more about our analysis, please look for us at upcoming conferences. We have an upcoming ACEEE summer study paper. You can also visit NEMA or NEA's website for a copy of the white paper detailing this analysis, and to find NEA's pump research final report, which we leveraged for this work. We're also going to be sharing this work with a number of other energy efficiency organizations, trade associations, and folks in the industry to continue to spread the word and develop interest in the energy savings potential of power drive systems across applications. So watch for us at an upcoming webinar or a conference.
Or feel free to reach out with any questions or comments. Thank you for your time.
Thanks.